Welcome to lecture series on digital electronics under EPG Pathshala. Boolean algebra is an algebra of binary number systems. Unlike traditional algebra, Boolean algebra supports only two numbers 0 and 1. It is very easy to understand and easy to learn. In addition to that, Boolean algebra has three basic operations. The first one is Boolean addition, Boolean multiplication and Boolean complementation. These are usually implemented using AND gate, OR gate and NOT gates. The digital system designer is always thinking about reducing the cost of the IC, reducing the size of the IC and increasing the speed performance of the digital system. Boolean algebra will definitely help the digital system designer to implement these parameters. Boolean algebra can be used to reduce the number of Boolean variables, number of logic gates, and in addition to that one can really reduce the size of min term and max term or product and sum terms. Definitely the use of Boolean algebra can provide many benefits to the digital system designer. In this session, we will explore the world of Boolean algebra. In this module, you will learn about the basic rules, laws and theorems of Boolean algebra. Further, the knowledge about the algebra can directly be used to simplify the Boolean expressions. Next thing, you will learn to convert the Boolean expressions into sum of products and product of sum. It is also possible to know the min terms as well as max term for the Boolean expressions. As the number of terms in the Boolean expression increases, it becomes difficult to simplify the Boolean expression using basic rules and laws of Boolean algebra. In the last section, you will understand how to use graphical method, that is Karnaugh maps, to simplify Boolean expressions. Let us begin with a simple question which correlates human thought with algebra. Is it really possible that human thought could be manipulated like algebraic formula? Think over. George Boole, the great mathematician, suggested that logical thought could be represented through mathematical equations. This is possible with the help of Boolean algebra. Year 2015 is widely celebrated as the birth centenary of the great mathematician George Boole. Boolean algebra was introduced by George Boole in his book Mathematical Analysis of Logic and an Investigation of Laws of Thoughts. Boolean algebra is the mathematical basis for all logic designs. Let us now talk about what the Boolean algebra is and how does it differ from traditional algebra. Boolean algebra is a set of rules, laws and theorems by which logical expressions can be expressed mathematically. Boolean algebra deals with two valued variables, that is true or false. Computers today are designed on the basis of Boole's laws of thoughts and was known as thinking machine. Claude Shannon was among the first to see this connection. Shannon demonstrated the applications of Boolean algebra in the analysis and design of digital logic circuits in the year 1948, which provided basic knowledge in the understanding of digital electronics. In Boolean algebra, binary variables can take either of two values 0 and 1 or true and false whereas in traditional algebra variable can have any value up to infinity. There are three basic operations: Boolean product, Boolean sum and Boolean complementation. Boolean functions are implemented using this combination of these operations. Addition and multiplication are two basic operations performed on binary variables. Boolean algebra basically operates on the binary variables as well as on the two values 0 and 1. Boolean algebra is a mathematical tool for specifying the logic function. It is also used for designing the logic circuit. In addition to that, Boolean algebra can also be used in analyzing the logic circuit. Many designers prefer to use this Boolean algebra with the help of simple logic gates. The AND, OR and NOT gates are normally preferred in implementing the Boolean expressions. This module we discuss a simple principle of Boolean algebra and its implementation for logic circuit. Variable names can be represented as single character or a word like variable A, B, C, D, X, Y, Z, sum, carry, reset, etc. are used in Boolean algebra. Logic gates can be used to implement logic functions. The three basic operators provide logic functions using AND gate, OR gate and NOT gate. Variables and complement are the terms used in Boolean algebra. Boolean function has at least a variable and a operator. A variable is usually an uppercase letter to represent logical quantity. A variable can have a value 0 or 1. Complement is the inverse of a variable and indicated by a bar or single quote. For example, complement of A is known as not A or A bar. Boolean expression can contain sum or product terms or combination of both as indicated here. Let us look at the product terms. Y is equal to A and B. Next equation could be Z is equal to C and D and E. Similarly, expression for 4 variables, that is W is equal to F and G and H and K. Boolean expressions are in AND form and these are all containing only product terms, whereas P is equal to A or B, Q is equal to C or D or E indicates Boolean expressions in some form. The Boolean expression f as a function of 4 variables A, B, C, D could be given as ANDing of A, B or with ANDing of C and D, which is shown here. Boolean algebra has its own set of fundamental rules which differ from real algebra. Let us now understand simple rules of Boolean algebra and study them in comparison with the real algebra. The Boolean addition is equivalent to OR operation and Boolean multiplication is equivalent to AND operation. 0 ORed with 0 is equal to 0 as well as 0 ANDed with 0 is also 0. 0 OR with 1 is 1. Similarly, 0 and 1 is 0. 1 odd with 0 is 1. Similarly, 1 ANDed with 0 is 0. 1 odd with 1 is 1, but note that in real algebra 1 plus 1 is 2. In 1 ANDed with 1 is 1 in a product form. Note that a sum term is equal to 1 when one or more inputs are 1 in the term. A product term is equal to 1 if and only if all the inputs in the term are at logic 1. The product term is equal to 0 when one or more inputs are 0. Similar to real algebra, the Boolean algebra also possesses certain well defined rules and laws. Let us now discuss the most important laws of Boolean algebra. Let us start with identity law in both product and sum form. Law 1, A and 1 is equal to A, that is a variable ANDed with 1 is equal to the variable itself. Since Boolean algebra has only 2 elements, we can now show the validity of these theorems by using truth tables. To do this, a truth table is built for each side of the equation that appears in the theorem. Then both sides of the equation are checked to see if they yield identical results for all the combinations of the Boolean expressions as well as values. Let us verify it. If A is 0, the product is 0. Similarly, when A is 1, the multiplication results in 1. Law 2, A or 0 is equal to A, that is a variable odd with 0 is equal to the variable itself. Substituting the values of variable 0 and 1, one can verify this law similar to the previous law. Let us discuss the null laws. Law number 3, A and 0 is equal to A, that is a variable ANDed with 0 will always result in 0. Law 4, A or 1 is equal to 1, that is a variable odd with 1 is always equal to 1. One can verify these laws by substituting the values of variables as 0 as well as 1. Let us study idempotent law. Law 5, A and A is equal to A, that is a variable ANDed with itself is equal to the same variable. Law 6, A or A is equal to A. A variable odd with itself is equal to the same variable. One can verify these laws by substituting the values of variable as 0 as well as 1. The inverse laws are discussed now. Law 7, A and not A is equal to 0, that is a variable ANDed with its complement result in 0 output. Law 8, A odd with complement of A is equal to 1, that is a variable odd with its complement results in 1 output. One can verify these laws by substituting the values of the variable 0 as well as 1. The double complementation law states that the double complementation of a variable is always equal to the variable itself. If A is equal to 0, complement of 0 is 1 and complement of 1 is 0. Thus, result is the same variable. Same thing is true for the value of a is equal to 1. Let us study some of the laws of Boolean algebra like commutative law, distributive and associative laws. Let us begin with the commutative law. The commutative law for product term is a and b is equal to b and a. It indicates that the order in which the variables are ANDed makes no difference on the result. Similarly, the commutative law for some terms is a or b is equal to b or a. The law states that the order in which the variables are odd will make no difference on the output. Let us now understand the associative law. The associative law in AND form is a and in bracket b and c bracket complete is equal to in bracket quantities a and b and with c. This law indicates that it makes no difference in what order the variables are grouped while dealing with ANDing of more than two variables. Similarly, associative law in OR form is a or in bracket b or c bracket complete is equal to in bracket a or b bracket complete ORed with c. This law states that while ORing more than two variable, it makes no difference regardless of the order in which the variables are grouped. One can verify these laws by substituting the 0 or 1 values to these Boolean variables. Let us now study the distributive law for product and sum forms. The distributive law is a and in bracket b or c is equal to a and b ORed with a and c. It indicates that ORing of two variables and then ANDing is equivalent to ANDing of first variable with the second and the third variable separately, then ORing these product terms. It also gives a sum of product form. The distributive law in OR form is a or in bracket b and c is equal to in bracket a or b bracket complete ANDed with a or c. This law is basically used to understand the process of factorization. In this, a common single variable is factored into product of sum form. Let us now discuss the absorption law. The AND form of the law is a ANDed with in bracket a or b is equal to only a, and the OR form of the law is a ORed with in bracket a and b is equal to a. Let us prove these theorems. Let us now discuss the absorption law. The AND form of the law is a in bracket a or b is equal to, let us write now right hand side, a ANDed with a ORed with a and b. As we know, a ANDed with a results in the same variable a. Therefore, we get a ORed with a and b. Further, the right hand side we can take A common. So, we get A ANDed with in bracket quantity 1 or B gives A and 1, since 1 OR with B is 1. Therefore, the result is equal to A. Thus, we have proved the absorption law. Let us prove the absorption law in OR form. A OR with A and B is equal to A and A plus A and B. This is a distributive law. The right hand side gives us A or A and B, since A and A is equal to the variable A itself. A and 1 or B, we can take A common. So, we get A ANDed with 1, definitely the result is A. Thus, we have proved the absorption law. In 19th century, the English mathematician and logician Augustus De Morgan proposed two theorems of mathematical logic, which are known as De Morgan's theorems. Let us now see these theorems. According to the first theorem, the complement of sum equals the product of complements. Let us see how these theorems are implemented using logic gates. The left hand side of the equation is viewed as the output of NOR gate with A and B as inputs. The right hand side of the equation is obtained by inverting both the inputs A and B, then putting them together through an AND gate. These two representations are equivalent. Let us now study the second De Morgan's theorem. According to the second theorem, the complement of product equals the sum of complements. Let us see how this theorem can be implemented using logic gates. The left hand side of the equation can be viewed as output of NAND gates with A and B as inputs. The right hand side of the equation is obtained by inverting both the inputs A and B, then putting them together through OR gate. These two representations are equivalent. In general, De Morgan's theorems can be extended for n variables. Complement of sum of variables is equivalent to product of complements of n variables. Similarly, complement of product of n variables is equivalent to sum of complements of n variables. Let us now take an example of De Morgan's theorem. Let us apply it for the Boolean expression. We have a term on left hand side consisting of three variables A, B, C as shown here. By applying De Morgan's theorem to the left hand side, we get double complement of A or B and C bar, which is equivalent to, now the double complement of the sum term will get cancelled and we get only A or B ANDed with complement of C. So, we can write right hand side as A and C bar or with B C bar. Let us now see the applications of De Morgan's theorem. The first simple application of De Morgan's theorem is to implement universal logic gates. NAND gate can be used to implement basic logic gates like NOT gate, AND gate and OR gate. For the implementation of NOT gate, we require single NAND with shorted input, whereas implementation of AND gate requires 2 NAND gates, whereas in case of OR gate we require in all 3 NAND gates. One can prove this using Boolean algebra and De Morgan's theorem. Similarly, NOR gate can be used to implement basic logic gates like NOT, AND and OR. One can prove these implementations using simple Boolean algebra and De Morgan's theorem. NOT gate requires a single NOR gate, whereas OR gate requires 2 NOR gates and 3 gates are required to implement AND gate. Let us now study the second application of De Morgan's theorem. For visualization of signal flow, one can really use De Morgan's theorem. In this case, let us connect the logic gates such that the gate with bubbled output be connected to the bubbled input gate. Similarly, the output without bubble are to be connected with a gate without bubble. So, thus in the first diagram we have 3 NAND gates connected as shown here with 4 inputs A, B, C and D and the output is Y. But we cannot comment on the nature of output depending upon the inputs. But if we modify slightly the above diagram, the right hand side will definitely be helpful to visualize the signal flow. In place of using the third NAND gate, we are replacing it by its De Morgan's equivalent. So, in place of NAND gate, we will draw bubbled OR gate. So, thus it indicates the output of the bubbled OR gate Y is 1 if either A or B is 0 or D or C is 0. De Morgan's theorem provides equivalent symbols for traditional logic gates. These symbols are shown in this slide. You can visualize these logic gates in either positive logic or negative logic. Similarly, we can have De Morgan's equivalent for buffer as well as inverter. De Morgan's theorem can also help to describe active or asserted levels of the signal. Signal names should be chosen to be descriptive one. There are 2 active or asserted levels, high or low. One can describe asserted high or active high or asserted low or active low. Typical signals are indicated here as either active high or active low. So, for example, for memory interfacing we prefer read bar, write bar, or maybe for microprocessor microcontroller we require reset bar, address, ready signal. We can have similar signals which are in an active high form as well. Let us now apply Boolean algebra to simplify some of the Boolean expressions. Example number 1, let us simplify the following expression. In this expression, we have 3 variables x, y, z, which are given below. Now, let us take z bar common from the second and fourth term. So, by taking z bar common, we get z bar ANDed with x OR with complement of x plus remaining 2 terms as shown here. As x OR with its complement results in 1. So, we get directly only z bar. So, in the third line, as you can see, z bar OR with x bar and y bar OR with y z. That is also equivalent to rearranging the terms. What we get in the line number 4 is the rearrangement of line number 3. Now, by using absorption law, we can show that y bar is absorbed from the 2 terms. So, thereby we get the final expression as x bar OR with y OR with z bar. Let us consider the next Boolean expression, which is once again a function of 3 variables a, b, c. But in addition to that, we are considering m as additional variable. So, in the first line, we have a OR with b bar c bracket complete OR with a or b bar c bracket complete ANDed with m. So, if you see, there is the first bracketed quantity is common. So, we can write in the second line, let us take a OR with b bar c common. So, we get 1 plus m, where m is any Boolean expression, any product term. So, in the third line, as we can say, 1 plus m is 1. So, therefore, we get only bracketed quantity as a or b bar and c. So, a Boolean expression is normally used to simplify the terms. Here you can see that out of 3 terms, finally we get only a single term. This example also indicates that we can simplify the Boolean expression by using rules, laws and theorems of Boolean algebra. The function is shown as a function of 3 variables x, y and z. The equation is given in the first line. Now, in the second line, we are just expanding the terms and then further simplifying it. So, after 4 lines, as you can see, we get the terms 1 OR with y OR with yz, that is also equal to 1 OR with yz, that is also equivalent to 1. So, thus the term is reduced to only a binary number 1. Since x is already existing in the expression, another term x can be added without affecting the value of expression, that is x OR with x results in only x. Let us now look at further simplification. So, we get on right hand side an expression with 3 terms. As we can see, we can absorb x bar from first 2 terms. So, what we get x OR with y bar bracket complete OR with x OR with z bar bracket complete or with yz, x or y bar or with z bar or with y and z. So, finally, in the fourth line what you can see is a sum term with 4 variables. Further, y or with y bar results in 1. So, what we can write is x plus z bar plus 1. So, anything odd with 1 results in 1. So, finally, what we get, the function is reduced to only binary number 1. These 3 examples proves that Boolean expressions can be simplified using rules of Boolean algebra. Let us now talk about duals. Theorems were presented in pairs. The dual of a function, that is interchanging OR and OR operations and replace ones and zeros with zeros and ones. So, one can obtain by interchanging them. The prime version of the theorem is obtained from unprimed version by swapping 0 and 1, and OR symbol is interchanged with AND symbol. Duality is important because it doubles the usefulness of everything about the Boolean algebra and manipulation of logic functions. A given logic function can be represented in a variety of different forms: canonical and standard forms, min terms and max terms, sum and product terms, sum of product terms, product of sum terms, sum of min terms and product of max terms. These forms are suitable for different applications. Identical functions will have exactly the same canonical forms. Now, we shall be discussing the canonical forms as well as standard forms. Before we discuss, let us now talk about few basic terminologies. Now, let us get familiar with different terms. The first, product term. Product term is a term containing all variables connected by AND, whereas the sum term contains all the variables connected by OR gate or OR symbol. Min term is a product term in which all the variables appear exactly once, either complemented or uncomplemented form. Max term is a sum term in which all the variables appear exactly once, either complemented or uncomplemented form. Thus, there is a difference between sum and max term, product term and min term. Standard form of Boolean expression facilitate simplification. The result after simplification provides more desirable implementation. Standard forms rely on two types of terms: product term and the sum term. The sum of product form is normally generated as a part of standard form. So, for example, a function of 3 variable ABC is given as sum of product forms containing certain variables as shown here. Another standard form of Boolean expression is product of sums. It contains 2 level implementation of Boolean expression. The first level is the ORing to provide sum term, and then at second level ANDing results in product term. Both SOP and POS are two standard forms of Boolean expressions. Both includes the sum and product terms for the two level implementations of Boolean expression. Any Boolean function can be expressed as unique sum of min term and a unique product of max term under a fixed variable ordering. In other words, every function has two canonical forms: canonical SOP, that is sum of products, or you may call sum of min terms, and canonical product of sums, that is product of max terms, which are shown appropriately with a suitable example. Boolean expressions can also be represented in canonical form of SOP and POS. In canonical form, each individual term involves all the variables either in uncomplemented or complemented form. The examples are suitably shown here. Let us now summarize the topics that we have studied so far. Boolean algebra is a mathematical tool for simplification of Boolean expression. A design problem can be converted into truth table, which relates the desired outputs for all combinations of inputs. Boolean axioms or rules help us to simplify the Boolean expressions. The duality principle states that every algebraic expression is deductible from postulates of Boolean algebra. Thank you.